what is a better way to conclude the workshop than presenting one of our own? I'm very glad to introduce my colleague, Corey Jones. I forgot the title.
Me too. I also forgot the title. Before I get started, I did Jumping wanted me to ask, is there anyone who would like a shuttle ride back to the hotel at the end of the conference? Or has everyone already checked out? Raise your hand if you would like a shuttle ride back.
Embarrassing?
No, I think it's totally fine. We just didn't need to know. We need to know.
No.
There's two? Okay.
Okay, two.
Good.
Because rather than one. That's embarrassing.
So the shuttle will leave what time?
10-15 minutes after this talk is over.
Okay, let's say 15 minutes after the talk, just to give you time to say goodbye.
Okay. And
Do I have time to eat?
yeah, and as the last talk of the conference, usually I would like to thank the organizers. I am myself one, so that's kind of awkward. Thank me. But let's a round of applause for the organizers besides myself.
Including we haven't come to yet. Really, Corey and Jianping did most of the work.
Mostly jumping. Okay, great. So let's get started. So I wanted to thank Chelsea for talking a lot about some of the things that I won't have to define now. Chelsea took care of all the definitions too for me. But quantum symmetries is kind of a buzzword that a lot of us like to throw around. But I want to talk about a very specific kind of concrete manifestation of what I mean by this, and a family of problems that I think are really interesting. So let's let A be an associative algebra. And what do we usually mean by symmetries of an associative algebra? Well, usually we were talking about the group of automorphisms. And this is a group, so we can talk about a group acting on our algebra by having a homomorphism from G to odd A. This is like our kind of classical notion of symmetry. But if you have an automorphism, you can actually construct a bimodule out of it by twisting the standard bimodule. So I can take A as an AA bimodule, keep the left action the same, but the right action, when I multiply, I'll apply the automorphism. So I'll have this kind of bimodule structure, A, B, alpha, C. So I kind of twist the right action buttons. Okay. So every automorphism, I can produce a bimodule. And in fact, this bimodule structure, if I think of it with the relative tensor product, remembers in some sense the group composition, the group of automorphisms. So there's a sense that you can think of bimodules as generalizing automorphisms. And these are kind of a traditional notion of symmetry, so maybe we can think of bimodules as a more general kind of receptacle for symmetry. Okay. So just like you had groups, the reason that you cared about groups as symmetry, because this was a group, so an action of a group on an algebra would be a homomorphism for me here. What kind of mathematical structure, algebraic structure does this thing have? And we can consider abstract whatever that thing is and talk about those acting on algebras. Okay. So I'll just come over here because this is the stuff that's going to be up for the whole talk. I'm not going to change this board. So BIM-A is a linear monoidal category. From my little subfield, we would just call this a tensor category. Tensor means linear monoidal, but I know there's a lot of people where tensor means something very specific, so I'm not going to use the word tensor unless I mean it. But yeah, so BIM-A is a linear monoidal category with the relative tensor product over A. That's our tensor product. That's our tensoring operation, our monoidal operation. Quantum symmetry, we can mean something specific, is a linear monoidal functor from an abstract tensor category to BIM-A. So this is an abstract monoidal category. And we can think of this as the category acting on the algebra in some sense.
Do you need it to be strong or anything?
Yeah, usually when I want, there's all kinds of versions. I would want this to be a strong monoidal functor, but of course you can consider the version where this is lax or oplax, and you get all different kind of flavors of symmetry. So this is kind of a general paradigm that you can do a lot of stuff with. And so just like, you know, you're often interested in classifying group actions on algebras, it's a really interesting question to try and classify tensor category actions on algebras, if you can. And there's actually a lot of, you know, this is a quantum because there's two quantumness, right? We like to use quantum where we're using non-commutative algebras, so that's certainly part of it, but also these tensor categories, generalizing groups, that's kind of also another quantum thing going on. But actually the problems that I care about are motivated by actual quantum spin systems and things like this in physics. And so there's at least three ways quantum's coming in to the story. Okay, three different ways. Okay, so that's kind of the general idea for the problem. I'll get more specific a little bit later about what kinds of categories I want, what kinds of algebras I want, and like what equivalence relations you might be interested in classifying. Okay, but we'll be mostly interested in fusion categories. When C is fusion. So there's a big definition soup here when we say fusion. I'll say what the words mean. So I want finitely semisimple. It should be rigid, which means it has left and right duals, as Chelsea explained, and a simple unit object. So, in the definition soup that Chelsea had, everything up to grading. We don't need gradings here, but we're also stipulating semi-simplicity here. Okay, so those are the two differences with what Chelsea was describing. And yeah, that's what we mean by a fusion category. Okay, so what are our examples here? So I'm always going to be working over C. A lot of the things, well, actually don't care about C. They're really I'm working over algebraically closed fields of characteristic 0. A lot of the things don't actually need characteristic 0, but some of them do. So I'm going to stick with just using C to be safe for this talk. So what are our examples? So from a finite group, you have a family of examples. You have things like rep G, which is the category of finite dimensional representations of G. The tensor product is the ordinary tensor product of group representations. You also have vec G, which is the category of G-graded vector spaces, where the tensor product, you kind of do a convolution product, and the gradients shift by multiplying by the group elements, right? So here, the simple objects are labeled by the group elements. They're one-dimensional vector spaces kind of fibered over the group elements, and then the fusion of the two elements is just the group multiplication. So, you know, if you're thinking of fusion categories or tensor categories more generally as generalizing groups, this is the one that really generalizes, kind of captures just the information of the group as an algebraic object in a tensor category form. Then, you know, what you can do is you can take this category here and you can twist it. So there's these, in the definition of monoidal category, there's an associative, which is a linear map that lets you move the parentheses around, like the associativity of the tensor product. There's an isomorphism. Here you kind of just using the boring one from vector spaces. There's an easy one to write down, but you can take that and twist it by a scalar, where omega is a 3 cocycle, valued in U1. Or sorry, that's a very physicsy thing to say. They say C times. And this category only depends, you know, on this up to cohomology. But to actually twist the associator, you pick some representative, and you can twist it out. And you know, this is kind of the first, you know, departure from just classical group theory. The first kind of category that doesn't fit into this framework on the nose. And more generally, you can have reps of a finite dimensional semisimple Hopf algebra. Finite dim, semi-simple. Let me put the word quasi here if I want to include all the examples, quasi-Hopf algebra. So all of these are actually examples of this for the appropriate finite dimensional semi-simple quasi-Hopf. Okay, but you can get a lot weirder with these things. There's these categories CGK, where this is a simple Lie algebra. And this is some natural number. So these categories have kind of implicitly appeared in Richard's talk this morning. So you can build them by taking representation categories of vertex operator algebras, certain vertex operator algebras, quantum groups at certain roots of unity, they look like the classical representation theory of the Lie algebra, but then they're kind of truncated at some finite level. You throw away all but finitely many, and then weird things ensue. But these are fusion categories. They only have finitely many simple objects. You should think of them as truncations of the classical theory in some sense. But these are an interesting family of examples. And something that kind of falls into this class, not on the nose, but is a subcategory of one of these things, is this category that we saw in Richard's talk, fib. There's actually a couple categories here, but there's two simple objects. So let me explain how this looks a little bit. Two simple objects. I'll call them the isomorphism classes at least. I'll call them 1 and tau. And they satisfy the fusion rule that if I do tau tensor tau, it's isomorphic to tau direct sum 1. Right? It's semisimple, so everything's a direct sum of simples. So when I tensor two of them, they should decompose, and here's the fusion rule here. And you can see that immediately these guys cannot look like rep H for any quasi-Hopf algebra H, because the objects, here are fundamentally vector spaces, and the tensor product is fundamentally the tensor product of vector spaces. And so in this case, there's a character. If I assign the dimension to an object, then it's kind of multiplicative and additive because the dimensions of vector spaces are with respect to tensor products. But here, if this was a vector space and I tried to compute its dimension, I would have the equation, d squared equals d plus 1. So its dimension would be 1 plus square root of 5 over 2, which is impossible. So these kind of things are really beyond Hopf algebra stuff, and they do fit into this framework. But there's many more. Richard was talking about near groups and stuff. There's a lot more exotic stuff beyond. But this is just to give you a sample of fusion categories kind of beyond classical group theory and even beyond Hopf algebra stuff. Okay. So those are kind of the examples that we have in mind. So let me give you a more formal version of this. I'm going to define an action of a fusion category C on an associative algebra. Well, this is just the kind of fancy notation. What it is just a strong monoidal functor. I'll put strong here because Chelsea asked. Monoidal, and it should be linear. I would have just said tensor, but strong monoidal functor f from C to bim A. So it's exactly what I was telling you on that first slide over there. But now I'm going to also tell you what kind of equivalence relation that we consider. C acting F on A is going to be equivalent to C acting on some functor G on B. So I have equivalence relation between two actions. So if there's an isomorphism from the algebra A to B, so that when I conjugate this monoidal functor from this and get a monoidal functor on B, then I'll have a natural isomorphism of monoidal functors. Okay, so that's the equivalence relation. So if there exists an isomorphism such that if I do, let's see, how do I write this? All right, F super phi this is monoidally naturally isomorphic, so monoidal nat iso to G. Okay, and so this is just transporting, if I have an isomorphism from A to B, I have an equivalence between AA bimodules and BB bimodules just by conjugating by the isomorphism. And so given one of these and an isomorphism from A to B, this is just kind of the transported monoidal functor by conjugating. So this gives me, these are both actions on B. And then so now I have two monoidal functors from the same source to the same target, and so I'm just asking for a monoidal natural isomorphism between those. Okay, so it's kind of like conjugacy and then a little bit of extra categorical stuff combined. And that's the natural, it turns out, the natural notion of equivalence, these classification questions. So there's an easy example, is suppose I have an ordinary group action. We have a homomorphism from G to odd A. Then doing this twisted thing I wrote on the first board actually gives you, canonically, a monoidal functor from vec G to bim A, just by twisting in the way that I said. And so actually, these actions, they actually generalize in a precise sense, the group actions. They're not just kind of analogs or something. Literally, group actions are a subset of all possible actions here. And what does this equivalence relation correspond to if I just had two group actions? It's what's called cocycle conjugacy, for those of you familiar with it. So this part, if I said this equals that would be conjugacy, but then having this little monoidal natural isomorphism, there's a little non-abelian two cocycle equation popping up. And that's kind of what this equivalence relation is generalizing. So equivalence generalizes cocycle conjugacy. Okay. And so the question is, classify fusion cat actions on our favorite algebras. So that's the quantum symmetries program that I would like to propose. And this is, fusion categories are kind of like the finite quantum symmetries, right? Categories can be big. They could be non-semisimple. They could be semisimple and infinite. They could be non-semisimple and infinite. They can be crazy. And so all that stuff is interesting, but just start small. Let's see what we can say about fusion categories. The smallest finiteness case. Finitest. Most finite case. Okay, any questions about that? Okay, good. So what do we already know? So some stuff, is kind of immediate, and we've been doing it since we started thinking about fusion categories as a field.
Actually, I have a question.
Yes.
So for this problem, do you have any faithfulness conditions or anything?
So good question. So the thing you're really after is you want these functors to maybe be fully faithful, perhaps. Maybe that's like an analog of an outer action. That would be like in the group action case, if each group element was acting by a non-inner automorphism, that would be the analog of asking this to be fully faithful. But fusion categories are particularly nice. You understand, if I have any tensor functor, it's always faithful at the level of morphisms. You might just lose fullness. You're always passing through a quotient. And then you have a fully faithful thing from the quotient. So for the special case of fusion categories, it actually doesn't really matter, because even if you're not fully faithful, there's internal, you're some quotient, and then you're fully faithful from the quotient, so you can kind of divide the problem up into classifying all the quotients of the fusion category and then classifying all the actions of the quotient, and that's the same story. So yeah, we don't really need to assume that, although in practice what you're most interested in is kind of a fullness condition, which corresponds to outerness here. And faithfulness is automatic just because it's fusion. Can't have any kernels in the Okay, good. So what do we know? So we already fully, in some sense, understand the semisimple case. If we say A is semisimple, so finite dimensional semisimple. Why do we already know that? Well, if I have a semisimple algebra, its category of modules is a semisimple category. And conversely, any simple category is semisimple, if and only if it's the category of modules of a semisimple algebra. So whenever you have an action of a fusion category on an algebra, it turns the category of modules of that algebra into a module category. And conversely, by Eilenberg-Watt's theorem, if you had an action, a module category on a mod, that gives you a tensor functor from C into bin. So actually, you're just doing module categories. This is just a fancy way of talking about module categories, at least under enough restrictions. And so we already understand this case. So if M is a mod, then a module category structure, module cat structure of C for C on M. Is actually just the same thing as an action on the algebra, right? And that's just because, from Eilenberg-Watt's theorem, any endo functor on the category of AA modules will be an AA bimodule. And so if this is acting, each element in my category gets assigned an endofunctor, and then that gives me my bimodule. So, because everything's semi-simple, I don't have to write down words like exact, left exact, right exact, whatever. Everything's semi-simple, so this is just true state. Okay. And so you can parameterize semi-simple actions, which is what I mean by this, actions on semi-simple algebras, by module categories. And then you have to actually pick the algebra that's realizing this category as modules of that, and that's the same as picking a progenerator in the module category, plus progenerator. So basically, this is a semi-simple category. This is the same as picking an object. So when I decompose it into simples here, it just contains every isomorphism class of simple at least once. That's all progenerator means in this case. Okay, and so I say parameterized because there's an equivalence relation, and the equivalence relation will be, okay, two of these actions are equivalent if these module categories are equivalent, and the equivalence takes one progenerator up to the other one, up to isomorphism. Okay, and this is considered something we know, because the very first thing someone does if you write down a new fusion category is they go try to figure out all the module categories. Every module category decomposes as a direct sum of indecomposables, so you just have to know the indecomposable module categories, and this is what people do in fusion categories when they find a new fusion category. They go try to work out all this stuff. So in some sense, I'm kind of considering from the classification question, like this is data that counts as solved. You already know this. Of course, there are some fusion categories where it's extremely hard to work out what this is, but for the ones that we're most familiar with, we kind of understand what this looks like. Or at least we have some kind of parameterization, so we kind of understand this case of actions on finite dimensional semi-simple algebras. Okay? It's just module category theory. So it's something we've been doing all along the fusion category. So let's try to boost this up a little bit. So we understand, actions on semi-simple algebras.
Can I
So,
ask a question
of
about,
course.
before we boost up, like go down? Like
Sure.
what if C is, what if A is commutative?
In fact, yeah, so there's a better commutative, there's a better equivalence relation, a weaker equivalence relation, which is Morita equivalence, where instead of asking for an isomorphism, you could put a Morita equivalence here, and then this would be, conjugate by the invertible bimodule. And up to Morita equivalence, all of these are commutative, right? And then, then that just means your progenerator just picks each simple object with multiplicity 1. But yeah, so that's a special thing in here. In the semi-simple world. In the non-semi-simple world, everything is more complicated. Yeah, so up to Morita equivalence, they all look like that.
Do they kind of recover the group case? Like in a semi-simplification, maybe I should just ask you this after.
Okay. Sounds good. Yeah. Sounds good. Okay. So how do I build new? So I understand, what's going on with semi-simple algebras. Maybe I can look for actions on algebras that are kind of built out of semi-simple algebras. So that leads us to the definition of a locally semi-simple algebra. So maybe I should say it this way: A is locally semi-simple if there exists a sequence a n I n through a n plus 1 dot where these are finite dimensional semi-simple, and it turns out you can choose the in to be injective, unital injective Homs, algebra Homs. And you have A is isomorphic to the inductive limit, the co-limit in the category of associative algebras. Okay. So the co-limit is defined by some universal property about a map out of the co-limit means I have a map out of each one of these that are compatible with the conclusions. And so if your A is isomorphic to a co-limit, that's what it means to be locally semi-simple. Now this is kind of the external definition. There's an equivalent internal characterization. Or, so this is just totally equivalent, there exists a tower, of subalgebras. with an finite dimensional semisimple, and the union is the whole algebra A. So these are equivalent. This is just kind of an external. This is useful if you're trying to construct one of these from scratch. I just give you a list of algebras and maps between them. But once you actually have one, you can identify these subalgebras with their images inside the limit, and then you can think of it as just subalgebras that are finite dimensional. Okay, so these are called locally semisimple algebras. So let me give you a couple examples. So here's the first example. So I'm going to let D be a natural number, and I'm going to set the nth algebra in this series to be the tensor product of the D by D matrices with themselves n times. Okay, which of course is, as an abstract algebra, is isomorphic to the D to the n matrices, like D to the n matrices. But I wrote it this way for a reason. Okay, so that's my nth algebra. Of course, that's simple algebra, so in particular semi-simple. So what's my IN map? Well, I'm going to take the matrix A in here, and I'm going to just tensor with 1 sub D. Okay, so this will give me something in the n plus first tensor factors. I just stick a 1 on the right factor, and that gives me a injective algebra homomorphism from here to here. And then I can just take the inductive limit algebra, and I get A is defined to be the limit of the ANs. And you can kind of think of this as an infinite tensor product. This is one way to rigorously define what you mean by an infinite tensor product of algebras, is this limit in this category. Okay, so this is one example. Let me give you another example that's a little more complicated. So the next example is, yes. So let me define Bn to be, I'm going to use that same D, but I'm going to take, let's see, D to the n of C, and I'm going to take the direct sum of these algebras. How many times do I want D times? So it's a direct sum rather than a tensor product. This, of course, is semi-simple. It's a direct sum of simple algebras. And I'm going to do an inclusion here, Bn into Bn plus 1. I'm going to send the, let's see, what do I want to do? I want to send A1 dot 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 A D to, well, let me give myself a little more room. A1, so this list of matrices goes to A1 dot 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 A D 0 0, comma dot dot dot. So it's the same thing in each factor. Okay, of course, this is a D to the n plus 1 by D to the n plus 1 matrix, because each one of these was a D to the n, and now I have D of them, along the diagonal, so this whole thing's D to the n plus 1 for each slot, and I do the same thing on each slot. Okay, so this gives me a unitary inclusion. I just keep going, and I can take B to be the limit of the Bn's. And so that's another example of a locally semisimple algebra. And let me do a third one, and then I'll stop giving you examples and tell you the point. So the third one, I'm going to define Cn to be m sub fn of C plus m sub fn plus 1 of C, where fn is the nth Fibonacci number. Okay. Now the map Cn to Cn plus 1, what I'm going to do is I'm going to take the pair A, B, so this is a Fn by Fn matrix, that's an Fn plus 1 by Fn plus 1 matrix, and I'm going to send it to B, comma, A, B, 0, So you can check that this works because of the recurrence relation for Fibonacci numbers. Fn plus 1 is Fn plus Fn minus 1. All of, this matrix has the right size, this matrix has the right size, so this is just a tower that you can build. And you can set C to be the limit. And then C. Okay, so these are all examples. It turns out that the A is isomorphic to B. So even though we built these things in totally different ways, using different summands, this thing and this thing, they're actually isomorphic as algebras. Okay, so that's the first kind of punchline, is that even though locally they look very different, right? I used matrix algebras with no centers here, and here I had centers at each level. Globally, the inductive limits are the same. So just because we understand the building blocks doesn't mean we understand the isomorphism class of the inductive limit. So maybe surprisingly, just because we understand semisimple algebras really well doesn't mean we understand their inductive limits, at least a priori, right? It's more complicated. So these two are isomorphic to each other, and this one's not isomorphic to those two. Okay, so the question is, so I'll write that down. A is isomorphic to B, and they're not isomorphic to C. How do we tell? Is there some kind of nice, the dream of when you're trying to classify things, right, is to come up with some invariants. This is what we all do, is come up with invariants to tell things apart. But the dream is to come up with invariants that give you a complete classification. Not only can you tell them apart, but maybe you can, sounds pipe dreamy, but maybe you can find some invariant that's computable that tells you that, if the invariants are isomorphic, then the algebras are isomorphic as algebras. That would be amazing. And it turns out that that's the case for these locally semisimple algebras. And the invariant is essentially just K-theory. So let me write some stuff down here. So we're going to take K0 base. So this actually appeared exactly, the version that I wanted actually appeared in John's last talk. What you do is you take the abelian monoid of finitely generated projective modules with direct sum. Okay, that's the monoid operation, and you take it, of course, up to isomorphism of modules. And then you do the growth and deconstruction. So whenever you have an abelian monoid, there's this kind of universal construction you can do that turns it into an abelian group. It's an analog of taking, like field of fractions, but going from monoid to group. And you lose some information. There's some quotienting you have to do and stuff like this. But you take the growth and dec group of this. So this is equivalent to what John called the split growth and dec group, where there's another version of growth and dec group for K0 for algebras where you use short exact sequences, and this is just if you take split ones, but that's the same as the same as. So this is the growth and dec group. Okay, so this is an abelian group. And this abelian group is definitely not enough to classify these algebras. Yes?
Wait, so you don't take projective modules?
Yeah, FGP,
Oh.
he means projective,
Yeah.
sorry. Yeah. Finite generated projective modules, yeah. This is an abelian group, and this is not enough to classify it. But it turns out that if you look at K0 plus of A to be the image of this stuff inside K0 of A. So I look at, this is a whole group. This is like, think about this as like the natural numbers, and then the K0 would be like the integers. Well, I'm saying take the image, take the natural numbers, take the image of this monoid inside this abelian group. That's what I'm going to call the positive cone. Okay, and it turns out that in this case of locally semisimple algebras, that this defines a partially ordered abelian group. Is a partially ordered abelian group. So one way to present a partially ordered abelian group is to tell me what the order is, and in this case, I'll say A is less than or equal to B if B minus A is in this cone. Okay, and it turns out that that defines a partial order. Equivalently, if you have a partial order, you can recover the positive cone by just taking the stuff that's bigger than or equal to 0. And those two definitions are equivalent. So one way to define a partially ordered abelian group is to give me a cone. You have to check it satisfies some properties and stuff. But this becomes a partially ordered abelian group. So it's more than just an abelian group. There's an additional structure on there, namely an order. And if you put that together, you get what's called the Elliot invariant. So it's the triple, so it's the abelian group K0 of A. You take this positive cone, which is the image of the projective modules inside the growth and decay group completion, and then you take the special element. So I wrote it as 1 sub A by law and convention, but what I really mean, if you're using the projective module language, take A as an A module, right? So the projection associated with the projective module is 1. And so take that equivalence class, that's a special element in here. It turns out it has the structure of what's called an order unit, which means that any positive element is less than some multiple of 1. And of course, that's just from the definition of finally generated projective modules that this is the case. But so this triple, so it's the ordered abelian group plus a distinguished element, which is an order unit, is called the Elliot invariant. And the theorem, which is due to Elliot, George Elliot, and I think around 1975, so this is not recent stuff, this is old stuff, is that two locally semisimple algebras are isomorphic if and only if their Elliot invariants are isomorphic. If and only if LA is isomorphic to L. Okay. So in these examples, the A, B, C examples, so A and B are the same, so that's good. I erased A, but we have B sitting here. Let me tell you what these Elliot invariants are. So L of B it's the d-adic rationals. So I take the fractions, the rational fractions that have a power of d in their denominator. So P is in Z, K is bigger than, is in natural numbers, union 0. And I think of this as an additive subgroup of R. So when I say this, I'm saying the order structure, the positive cone, is just the positive ones of these, like in the usual order structure on R. That's what I mean when I write this way. So as an abstract abelian group, it has some characterization. It's not finally generated. But the positive structure is, the order structure comes from a subgroup of R, and then the distinguished thing is 1. And 1 in here is the distinguished element. Okay. So that's what the Elliot invariant is. This is the abelian, the ordered abelian group. It's a linear order. What is it for that that C, the one that used Fibonacci's? For C, we have that the Elliot invariant, so let me write it this way, it's Z plus Z adjoint phi, which I'm thinking of as a subgroup of R. So this is 1 plus the square root of 5 over 2. It's golden ratio. Okay, and so I'm taking integral linear combinations of phi and 1 inside R. As an abstract abelian group, this is just Z plus Z. It's a free abelian group of rank 2. But the order structure is highly non-trivial because the things that we're calling positive are the things that are positive as a subset of R. Okay, so if I forgot about the order structure, this would not, you can see this isn't going to be giving you much information. This K0 group is the same as the K0 group of, say, C plus C, the two-dimensional algebra C plus C. I wouldn't be able to tell if I just looked at K0. But with the order structure, you see it's highly non-trivial. And then 1 is the... Okay, so you can see these are not, isomorphic. Even if you didn't have the order structure, you could see these are not isomorphic because this is now finally generated, that is. Right, but with the order structure, you can really see they're really quite different as well. Okay, so we have these are really combinatorial in a sense. There's order theory there, but the way you compute them is combinatorial. So these are kind of combinatorial invariants that give a complete classification of these algebras. So maybe we can extend these combinatorial invariants to include the additional action of a tensor category on the algebra. So maybe if we have a tensor category acting on the algebra, we can come up with some Elliot invariant of the action, which has the same flavor to this, maybe K-theoretic in nature, and hope for some kind of theorem like this. Okay, and so that's what I'm going to tell you about today. Let me check my time. So what am I going to? 27 or something like that?
Yeah, 10 minutes.
10 minutes? Okay. So let me just go ahead and very quickly tell you the what the invariant is. So if C is a fusion category, we can define C hat to be a small category where the objects are Morita classes of indecomposable, separable algebras internal to C. So this is equivalent by Ostrich's theorem to just saying, you can make the objects indecomposable module categories if you want to. But I like to use algebra objects for a specific reason. And then the morphisms between two of these are just going to be the isomorphism classes of bimodules between the algebras. So HOMs between, if I have a Morita class of algebra P and a Morita class of algebra Q, is just going to be PQ bimodules in C up to isomorphism, just the ordinary notion of isomorphism bimodules. Okay? And so these, this is an I can take the direct sum of two bimodules, so this is kind of an added, this is an abelian monoid, and it has an n-linear basis of the irreducible bimodules. Because I'm in semisimple world, everything is nice semisimple. These categories of PQ bimodules are semisimple, so there's a nice n-linear basis. And then composition is just going to be relative tensor product. If I have a PQ bimodule and a QR bimodule, then I just take the relative tensor product, and that's the composition of them. Okay, and then so this thing, that's what C hat is. So C hat is just that. It's kind of like a fusion ringoid, or maybe a fusion ruleoid, because I'm not adding inverses. There's a finite collection of objects, and between them there's kind of like a canonical n basis, which is like the simple objects in your category, but going from A to B, and then when I compose them, they decompose into simples. So it's kind of right down this category is very much a combinatorial type thing. It's of the same flavor of a fusion rule, or a fusion ring, or fusion decomposition, but it's an oid, right? There's different sources and targets, and those are indexed by the Morita classes of indecomposable algebra objects. Okay, so if I had a little bit more time, I might give you an example. Well, maybe I'll do that anyway. Good. Come on with the example. Okay, so let's have C be vec ZP. So P is going to be prime. Then C hat is going to have two objects, because there's two isomorphism classes of indecomposable algebras, the trivial algebra and then the group algebra. So let me just write this G equals ZP. Those are the only algebras. From this to itself, of course, I have, this is just arrows are labeled by G. Okay, they're labeled by the objects in the simple the elements, the simple objects in vec ZP, which are the elements in my group. Here, these are labeled by these are elements in G hat in the dual group. They're irreducible representations, right? This is the dual category to this category under the one module category. And then I just have one arrow in each direction, which you can call x, maybe x bar. And you have the relation that if I do x times x bar, so if I compose this with that, it's the sum over all the G and G. And if I compose it the other way, it's the sum over all the irreducibles in the other direction. X bar is the sum over maybe omega in G hat. Right? Because really when I draw this picture, these are basis elements, so the real category will have n linear combinations of these. So there's I can take sums of these arrows formally. And then the rules, if I compose two G things, I just do the group multiplication. Here I just do the dual group multiplication there. So the only interesting one is these compositions. And so this is an example. If I put a more complicated G, you can work out what this is. It's just more complicated. You have to look at the subgroups and their cohomology, and there's all kinds of complicated computations you can do. We know how to do them. It's just there's not like a closed formula for what these fusion rules look like at the moment. it involves complicated induction, restriction, representation theory stuff. But if you put a G in there, in principle, we know how to compute these things. So this isn't super complicated. But in this prime case, you can just kind of write it down like that. And for fib, there's only one object. Fib only has one indecomposable algebra object. And the arrows, there's just two arrows. It's namely 1 and tau. So this becomes really simple in the case of fib, because you just get the fusion ring back, because there's only one object. Okay, so in some cases, it's really just the fusion ring, but in general, you have to take into account all the other module categories in algebra. So let me define the generalized, the extended Elliot invariant. If you have C acting on an algebra, F, you can define F hat, it will be a functor from C hat up to partially ordered abelian groups. Okay, and if I had more time, I would just tell you what it is. It's not super hard. If you take an algebra, if you have an algebra object in my category, I'm realizing my category has bimodules, I can just take the image of the algebra object. That will give me a new algebra in the category of AA bimodules, which of course just is an algebra. It's an algebra containing A, right? So the objects here are algebra objects in C. I just push them forward, and then I take the Elliot invariant, or the partial ordered abelian group of all those things. When I have a bimodule between algebras, well, tensoring with that bimodule gives me a map from finitely generated projective modules to finitely generated projective modules, so it induces a morphism between the ordered abelian groups. And the way to say that is just it's a functor. And because of the conventions I pick with composition, it's an op. But you could pick different conventions and make it not be an op. It's fine. But that's what this F hat is. And so you can define L of the action to be the pair. So it's F hat, which is a functor from C hat op to partially ordered abelian groups. And then you still have to remember that special element in F hat of 1. There's always the trivial algebra. That just will recover the Elliot invariant of A. And you just have to remember that one special thing in there, and then all the rest of that. So let me now just quickly tell you the theorem, and then I'll finish. So theorem, and this is joint work with Chen and Roberto, Hernandez, Palomares, and myself. So if C is an inductive limit action, I'll tell you what that means in a second. So let me say it this way. If CF and CGB are inductive limit actions, on locally semisimple algebras A and B, then they're equivalent. I think I use a double sim. If and only if the Elliot invariants are the same. So this is a direct generalization of the original Elliot theorem. So I snuck in this word here, inductive limit actions. What does this mean? This isn't actually true for arbitrary actions. Okay, you need this additional condition, which means that there's a finite dimensional filtration where C is preserving the things at each block. Now, I don't have to pick one. There could be many different ones. I'm not saying that's not part of the structure, but it's just the existence of one. So it's kind of like locally semisimple means there's this finite dimensional filtration. I'm asking for the action to have one too. So a better word might be like a locally semisimple action of a fusion category on a locally semisimple algebra. So I stuck that word in there. The action itself has to have this finite dimensional decomposition. But then when you have that, then you get this theorem. And in fact, all actions we know of all fusion categories have this property, not because we think they all do. It's just those, if you're going to construct it, this is how people construct actions. So somehow this covers all the actions that we actually know about. For fusion categories, for groups, there are some ones that aren't of this form. We know of some examples. Okay, but anyway, I'm probably out of time. Right on time. Let me tell you one last corollary. Is that there exists a unique, so you can use this theorem to show there's a unique inductive limit action of that fusion category fib on that C algebra I talked about, of fib, on that C algebra, which was the one whose K theory on the LSS algebra with K theory. The Z plus Z. So that weird one, the third one I wrote on the board, there's actually a unique action of this type on there, and you can prove that using this theorem. Okay. So anyway, that's the end. I'll stop there. Thank you.
Any questions or comments?
Yeah, so what happens if you consider other algebras, like algebras of finite representation type, for example?
So I don't know. These are all very good questions. So historically, these questions have been investigated in the context when these algebras are what are called operator algebras, or C-star or von Neumann algebras, where they have some analysis flavor to them. And that's almost everything that's known is there. And so this is kind of the first step, and that was my background, but this is the first step in kind of taking that in a more general algebraic direction. But as far as I know, like literally nothing is known outside of this and the semisimple case. But yeah, no, that's a great question. I don't know. Yes?
Can you explain why the only separable algebra objects in C are those two?
So the only connected separable algebra objects are, so remember I'm carrying about stuff up to Morita equivalence. So the only Morita classes are given by this. Connected algebras, which means that the multiplicity of one inside there is 1, everything's Morita equivalent to one of those. So if I can parameterize connected algebras in here, then I win. Those are parameterized by subgroups and second cohomology classes on those subgroups. And ZP has only 2 subgroups, the trivial one and the whole one, and there's no so that's why I get 2, and there's no cohomology H2 on this one, so that's all we have. There's no twistings. So these are the only connected ones, so therefore they're the only possible ones, and they're not Morita equivalent to each other. So in general, it's subgroups and 2 cocycles up to a kind of conjugacy equivalence relation. Yeah.
Wait, 2 cocycles with values where?
In C times.
Okay.
Yeah, not in
Because-
Z. Sorry, you're probably thinking in Z. Yeah. There's a dimension shift in C times.
Any other questions or comments? If not, let's thank Corey again. Well, I would like to thank all the participants, because without you, of course, these workshops won't be successful. And it was really, from my point of view, very engaging workshop, because even today, this is the last talk, and the participation itself tells how good it was. And as this workshop series, we have standardized things, and you will get a survey to let us know what works best. If you have any suggestions for us to improve next time. In particular, we have introduced this professional development session into the workshop for the first time, and we would like your feedback whether we should have, if it was beneficial, and whether you want us to continue this, as a feature in this workshop series. And with this, I thank all of you and have a safe trip back, and we'll be in touch. And of course, those of you who are supported by the NSF grant, please do the necessary paperwork. We have no role to play once we tell how much you will get. The university does the rest. So please respond to Mary if she has any questions or needs any paperwork from. Okay. Thank you all.